entitled Advanced Features Part 1, and there's a lot to cover in this module, and I'm going to jump right into it in just a minute, but I want to first explain my use of the name Advanced Features that I gave to Module 7 and 8, because I don't want what I present here to be misrepresented as truly complex features. I use the term Advanced Features here loosely because in reality, the features presented here in this module as well as Module 8 are really no more advanced than features presented in previous modules. In fact, compared to GI solutions and things like image sampling, which were explained in the first two modules, these features should actually be much easier to grasp. So I call all of these features advanced because while they're not advanced in terms of complexity, they really should be reserved for a time when you're at an advanced level of work. Otherwise, you're probably just going to make things more difficult for yourself. Everything that I've discussed in these modules has been presented in a very precise order, in an order that starts with fundamental concepts, i.e. critical settings, and then builds progressively upon those concepts in a way that maximizes understanding and minimizes confusion. And I've tried to do this by minimizing variables whenever possible. For example, even though this is a class based primarily on lighting techniques, I kept lights out of the discussion until Module 6 because they simply weren't necessary in a discussion on image sampling, HDRIs, QMC, GI, etc. As another example, I haven't talked about the VRay physical camera up to this point because this particular feature can completely change the way illumination in your scene appears. If I gave this completed scene to a VRay user with very little experience and then asked the user to replace the standard camera that was used to render this image and replace it with the VRay physical camera, I might get an image like this back, or maybe something like this. So until you have a good understanding of all the other things that have been discussed in the first 6 modules, you probably shouldn't try using things like the VRay physical camera because you'll just be making things hard on yourself. It would be like putting the cart before the horse. Now, with that said, the first feature that I want to talk about is progressive path tracing. There are so many great things about this program, VRay, and I think one of them would have to be the wide range of tools available to get the same end result. In this case, progressive path tracing is certainly another tool that should not disappoint. It's a rendering method that uses the light cache algorithm to progressively render the final image all in one step, bypassing all of the normal steps that are processed individually one at a time. Steps like primary bounce, secondary bounce, image sampling, depth of field, caustics, and so on. So instead of creating these steps individually, it processes everything all in one larger step. Now, there are 2 things that make this rendering method such a great choice for your work. First, there are very, very few settings that you need to worry about when using this method, and therefore it's very simple to use. I'll explain what these are in just a moment. The second great benefit of this method is that you get a final rendered image the moment you start rendering. What I mean is that because there's only one step in the rendering process, and since the entire image is rendered all at once, you literally have a final image rendered almost instantly. The only caveat is the rendering quality is poor at first and progressively improves over time. When the rendering has reached a sufficiently high enough quality, you can stop the rendering and immediately use the rendered output. Now, since progressive path tracing uses the light cache algorithm, it should be no surprise that this method is enabled within the light cache rollout. It's one of the 4 available light cache modes, and when enabled, the light cache interface isn't changed and nothing is ghosted out. But as I said, there are very few controls that guide the render quality of this method, and the only setting that really matters here in the light cache rollout is the subdivision setting. This setting still represents the square of the number of rays or paths that are traced, hence the term progressive path tracing. If you remember from Module 2, I said that a good value for production renderings would be values from 1000 to 2500. And in Module 4, I said that for animations, this might need to be substantially increased because the sampling is spread out over the course of the entire animation path. Well, when progressive path tracing is used, this value should really be set much higher. But a big determining factor on just how high to set it is the rendered image size. And to demonstrate this, I'm going to render this view from this particular scene at 100 pixels by 100 pixels. Notice the rendering time. And now I'm going to render the exact same thing at a screen size of 300 by 300. Notice the rendering time didn't change. And once again at 600 by 600. still the same. This is because the same number of rays or paths will be traced regardless of the rendering size. So the higher the resolution, the more number of rays that you really need to be traced. So how do you determine the number of rays? You could always just set the subdivision at a really high value to a maximum value of 65,000 and let the rendering process continue until you get the image quality you need. But just so you aren't blindly using values without knowing what subdivision value will really produce nice, smooth, noiseless images at varying image sizes, you will need at least 1,000 samples for every pixel in your rendered image. And to put that into perspective, consider the following example. If you use a subdivision value of 1,000, then of course the number of rays being traced is 1,000 times 1,000 or 1 million. Likewise, if you render an image 1,000 pixels by 1,000 pixels, then of course your image will have 1 million pixels in it. Therefore, using a subdivision value of 1,000 on a rendering of this size means that you're going to have one sample ray taken for each pixel. If you render with such a configuration, clearly the image is not a good one. And as I said, you really need something in the neighborhood of 1,000 rays per pixel to get decent noiseless quality. So to figure out what your subdivision value needs to be, determine the number of pixels in your image, multiply this number by 1,000, and then take the square of that number. That number is what you'll need for the subdivision value. So in this example, I have 1 million pixels on my screen or in my image, and so multiplied by 1,000, I know that I'm going to need 1 billion rays. The square root of 1 billion is 31,622. So that's the value I'll need when rendering an image size of 1,000 by 1,000. Now, since the subdivision value represents the square root of the number of rays traced, doubling the rendering size means that you're going to need to quadruple your subdivision value to get the exact same rendering quality. This in turn quadruples your rendering time almost exactly, in fact. Now, there's a few more really important things to remember about progressive path tracing. First, there's numerous settings that are ignored when this method is used. For example, image sampling is not even conducted, so the image sampler settings have no effect on the rendering. Next, subdivision values for blurry reflections and refractions are ignored, as well as subdivisions for shadows. And notice here when I render this region using light cache in single frame mode, a subdivision value of 1 for the sun's shadows results in a great deal of noise. Well, when I switch to progressive path tracing and use a decent subdivision value, I get noiseless shadows. Also, the anti-aliasing filter plays a large role in the noise that appears in your rendering. Using a filter such as the default area filter will produce nice renderings, but very sharp filters like Catmull ROM or very blurry filters such as the soften filter will add a large amount of noise and should therefore never be used. Your best bet or your best choice would be to disable anti-aliasing altogether, and by doing so you'll still get anti-aliasing, but it will be handled within the light cache algorithm, so your final rendered image will still look fine without this option enabled. A few more things. With progressive path tracing, you can't render to elements, which means you can't render individual channels such as reflection channel, refraction channel, alpha channel, etc. Also, within the QMC sampler rollout, the noise threshold value is really inconsequential because noise is controlled solely through the light cache subdivision value. And with the QMC sampler rollout, remember never set the adaptive amount to 0.0 because doing so can cause VRay to crash or freeze up. And one final thing, when you're using progressive path tracing, make sure you avoid panning around and zooming in and out of the default 3ds Max frame buffer, i.e. the render window. Doing so can also result in VRay crashing or freezing up. So instead of using the 3ds Max frame buffer, try using the VRay frame buffer instead. You won't have the same problem with the VRay frame buffer. And this brings us to the next feature I want to talk about, the VRay frame buffer. The VRay frame buffer is a render window just like the 3ds Max frame buffer, but it contains far more power and function. This feature even contains its own rollout, which of course is where the feature is enabled. So when you render with the VRay frame buffer, the 3ds Max frame buffer is disabled and you're shown a very different render window. The first feature here in the frame buffer that I want to point out is my favorite feature, and it's enabled through the far right icon. It's called Track Mouse While Rendering. What this feature does is it allows you to use your mouse to specify which buckets get rendered first. So I'll demonstrate using the scene, and when I render, notice that the buckets are rendered in order of proximity to the mouse cursor. So as I move the mouse around, the buckets that are closest to the cursor get rendered first. When I first learned of this particular feature, I started using the VRay frame buffer for every job, and I'll never switch back just because of this one feature alone. What makes it so great is that unlike a render region, which obviously allows you to specify a certain area of your screen to render by itself, this feature essentially lets you define multiple render regions. Not literally, but by moving the mouse from one point in your rendering to the next, you're in a sense defining a region one bucket at a time. This can come in very handy when you have more than one specific area of your rendering that you're trying to see rendered before others, which might be something you would want to do if you're conducting test renders or to simply ensure that you know as early as possible whether or not your problem areas in your scene will render okay. The longer your renderings take, the more this particular feature becomes a handy one. The next feature within the frame buffer that I want to point out is the render elements drop-down list, which lists all the various render elements that you can specify in the Render Elements tab of the Render Scene dialog box. This is a great way to view all the individual render elements without having a multitude of additional render windows appear on your screen, one for each particular rendering element. Render Elements, remember, is a tool that can be used for compositing, or a tool that you can use to help analyze what's going on in your scene in terms of GI, reflection, refraction, etc. If you're doing composite work and you need to render each of these elements to a file, simply enable the Save Separate Render Channels option, and when you specify a file type and save location, these additional images are created during the rendering process. The last great component of the VRay frame buffer that I want to point out is the tool set at the bottom of the frame buffer, which you can use to make simple adjustments to the final rendered output. And the three big adjustments that you can make before or after a rendering is conducted is exposure correction, color curve correction, and color level correction. To make any of these corrections, you must first click the Show Corrections Control icon, and the render that appears is where all three correction types are made. To view each individual correction type, you must first click their respective icons. Use Color Levels Correction, use Color Curve Correction, and use Exposure Correction. Now with these three options enabled, you can make and view the adjustments. The slider along the top of the Color Corrections window controls exposure. So as you can see, you can make slight adjustments to exposure to compensate for non-ideal lighting setup or for inadequate exposure adjustments made within the color mapping rollout. The sliders below the graph are the color levels corrections, which simply provide the min and max color level values for the image. The graph at the bottom is where color curve corrections are made. Here again, simple adjustments to compensate for the problems with the final rendered image can be made here. Also, you can use a wheel mouse to pan around and zoom in and out as you click and drag on the Bezier curve. Well, that's all I want to cover with the VRay frame buffer. I highly recommend using it over the 3ds Max frame buffer, especially when rendering larger images. So let's move on to another great feature, the VRay Physical Camera. Well, the VRay Physical Camera is designed to provide all the controls and all the functions of a real-world camera while giving you the same type of image. And this assumes, of course, that all other light settings are kept at real-world values. For example, to get real-world results with this camera on exterior scenes, at least as seen by the program designers, you should use the VRay Sun. You certainly can achieve a similar look, similar appearance using numerous different lighting configurations, including standard or photometric lights. However, if you're trying to equate the VRay Physical Camera settings that you use with what you would see or what you would use with the same settings on a real camera in the real world, then you can most easily do so by using other features and other settings that attempt to mimic real-world lighting. So another example besides the VRay Sun is linear color mapping. Color mapping is like exposure control, but since the VRay Physical Camera has exposure control built into it, you shouldn't compound or extenuate this effect by using additional exposure control, i.e. color mapping. By leaving the color mapping feature set to linear with its default values, you're technically using exposure control, but linear essentially has a neutral effect. So I recommend setting color mapping to linear when using the VRay physical camera. One more note about real-world results. The VRay Sun multiplier, which is set to 1.0 by default, provides far too much illumination for most scenes when a standard camera is used, unless its intensity is offset in other ways, such as color mapping. But when you use the VRay physical camera, the VRay Sun multiplier of 1.0 is designed to yield real-world lighting. So the bottom line is, with a VRay physical camera, you can't expect to get real-world results in your renderings if you use abnormal skylight, abnormal primary bounce multipliers, and so on. Alright, so let's look at what the VRay physical camera is all about. Well, most low-end cameras, most inexpensive cameras, don't have many settings on them, but high-end, expensive cameras, both film and digital cameras, usually have a multitude of settings that not only provide greater control, but also greater difficulty in their use. And unless you know what settings to use in the real world, you probably won't have much luck getting the results you want with the VRay physical camera. It's controlled by the same settings, and those settings are just as difficult to understand. I mentioned at the beginning of this module that I entitled this module Advanced Features, despite the fact that most of the features in this module are really less difficult than most features presented in previous modules. The VRay physical camera, however, is certainly one feature that can truly be called advanced. And because it's such a complex feature with so many controls, what I want to do here is highlight the really important ones. You can certainly use all the controls at some point in your work to create unique or unusual effects, but like all areas of Max and VRay, there's some controls that must be considered for every project and other controls of lesser importance that can really be disregarded for other projects. You can take a year-long college course on photography and still be considered a novice. So again, the point here is just to understand the fundamentals of photography and cameras that will make it possible to use this VRay physical camera successfully. When you take a picture with a real film camera, a device called a shutter opens temporarily, allowing light to pass through it and strike the film that is later developed. But before the light can pass through the shutter, it has to first pass through a lens, and that lens has an opening called an aperture. The longer the shutter stays open and the larger the aperture size, the more light that can pass through and the more exposed the film becomes. So for every shot that is taken, the shutter speed and the aperture size play a major role in determining how exposed a film becomes. But there's a third major ingredient, and that's film speed. The faster the film, the faster it becomes exposed when it's struck by light, and therefore the less light that is needed to expose the film. And there's a great analogy about how all three ingredients interconnect to control exposure, and it should make understanding what I'm talking about much easier. Imagine filling a bucket with water. When you fill a bucket with water, you pour the water in at a certain speed, and the water falls with a certain thickness to its stream. And regardless of how fast you pour the water or how large the stream of water is, the bucket is of a fixed size and you need a certain amount of water to fill the bucket. And the same can be said for film. It doesn't matter how large your aperture is or how long your shutter speed is open. All that matters is that the correct amount of light strikes the film. So the aperture size can be compared to the stream size, and the length of time that you pour the water can be compared to the shutter speed. And lastly, the size of the bucket can be compared to the film speed. So for any given film speed, a precise combination of shutter speed and aperture size is needed. And of course, variations can be made from this combination. However, the farther you stray from the correct amount of exposure, the more erratic your exposure might become. Now, most consumer cameras have standard shutter speeds that can be set, which is simply the amount of time that the shutter is open. Shutter speeds are measured in seconds or fractions of a second, and they usually start at a very slow value, such as 8 seconds, with each successive speed being twice as fast as the previous speed. So a typical range of shutter speeds will contain speeds like 8 seconds, 4 seconds, 2 seconds, 1 second, half a second, a quarter of a second, and so on, all the way to a very fast shutter speed like 1/1000th of a second. An 8-second shutter speed is considered extremely slow and often requires a very small aperture size or a very slow film speed to prevent overexposure. And on the other extreme, 1/1000th of a second is considered extremely fast, and it usually requires a very large aperture size and a very fast film speed to prevent underexposure. This kind of film speed could be used for capturing fast-moving objects without the effect of blurring. The average consumer camera has a shutter speed of about 1/125th of a second, which is really necessary to prevent the typical user from blurring the exposure due to things like handshake. If a shutter is slower than this, i.e. in the 1/60th of a second or slower range, then the user should really be using a tripod because any movement at all in the camera is going to result in a blurring of the exposure. With the VRay physical camera, there's a control for shutter speed and it's entered as a denominator. In other words, for a shutter speed of 1/500th of a second, simply enter 500. For 1/60th of a second, enter 60. For a shutter speed of 1 second, enter 1, and for a shutter speed of 2 seconds, enter 0.5. Well, that's shutter speed in a nutshell. Let's look at another term in photography called focal length. The focal length is the distance from the lens to the film. The smaller the distance, the wider the field of view, and the greater the distance, the more telephoto the view. Lenses with a focal length of 35 millimeters or less are considered wide angle, while lenses with a focal length of 100 millimeters or greater are considered telephoto. So a 200 millimeter lens will provide twice the zoom power as a 100 millimeter lens, and hence make the objects appear twice as big or twice as close. At the wide angle extreme, objects are distorted from the way they're seen by the human eye, and at the telephoto extreme, objects are not so much distorted as they are blurred, when at least not in the range where objects are in focus. Well, the human eye sees objects similar to the way objects are seen with a 50 millimeter lens, and by this I mean what you would see with one eye open, not both. So a 50 millimeter lens is considered normal and is what you would get most often when you purchase a camera. So within the VRay physical camera settings, place your focal length at 50 millimeters if you want the quote-unquote normal view with your camera. Now let's look at aperture size. First of all, if you were going to buy a 35 millimeter camera, which is the typical consumer camera, you're actually buying a camera that uses a film size of 35 millimeters. And this has nothing to do with the lens focal length, which was just discussed. This is because really any lens can be attached to any camera. So when you hear things like a 28 millimeter lens or a 300 millimeter lens, don't confuse this with film size, which by the way is also a setting found within the VRay physical camera. I recommend leaving this particular value at 35 millimeters because this has long been the norm in photography. While all lenses are referred to by their maximum aperture size, i.e. the largest opening that they allow, they're made so that the user can control the amount of light that passes through the aperture by controlling the size of the aperture. But instead of providing control that would be based on a percentage of the maximum aperture size, such as 90%, 80%, or 70% of the aperture size, the controls simply allow the user to cut the amount of light in half by cutting the aperture size in half with each successive reduction in aperture size. The term that's used on a lens to control aperture size is known as f-stop. The f-stop is simply the ratio between the aperture diameter to the focal length of the lens. For example, if a wide-angle 28 millimeter lens had an aperture size equal to the focal length, then it would be called a 28 millimeter f1 lens and would allow 100% of the light that comes through to strike the film. The user could cut the amount of light striking the film in half by stepping down the f-stop to a value of 1.4. The light could be cut in half again by stepping down to a value of 2.0. Shown here are the standard f-stop values for the average camera, with 1.0 allowing the most light in and 22 allowing the least amount of light in. So within the VRay physical camera, the same f-stop control is provided. It's listed as an F number, which is just another name for f-stop. Now, it's not so critical for an explanation of the VRay physical camera, but I thought it would be interesting to mention that not all lenses have an f-stop of 1.0 or 1.4. In fact, few lenses do, and it's because the cost of the lens and the weight of the lens begins to skyrocket as the aperture size increases. This has to do with the complexity of housing a lens with such a large aperture, but the important thing to remember is that a lens with an f-stop of 1.0, 1.4, and 2.0 would be considered fast because they allow a lot of light in really fast, and fast lenses are expensive and not the norm. A lens with an f-stop of 2.8 would be considered a normal lens, and it would have a maximum aperture size of 1/8 of the focal length. And just to make this easier to see graphically, here's a table showing the relationship of f-stops to the diameter of an aperture to the area of an aperture for a 50 millimeter lens. So if you look down the column on the right showing the area of aperture, you can see the doubling and the halving going on up and down the column. You can also see how the big f-stop numbers equate to smaller areas. Okay, well, so far we've looked at shutter speed and f-stops, two of the three major controls that affect exposure within a camera. Of course, film size was mentioned as well as focal length, which is a component of the f-stop ratio. The third major ingredient to the exposure of film is the actual film speed. Film is made with a variety of speed, defined by how fast it becomes exposed when it's struck by light. But the speed of film is based primarily on how large the grains of silver are lining the surface. And this is because the larger the grains of silver, the more sensitive the film is to light, and the faster it becomes exposed when struck by light. The smaller the grains of silver, the less sensitive the film is to light, and the slower it becomes exposed. The quality of the developed film is directly related to this grain. So film with large grain will be of lesser quality than film with very fine grain. High quality film, i.e. slow film, like the kind used for portraits, is made with very fine grain, which makes it less sensitive to light and requires more light to expose it. Film with large grain is more sensitive to light, so it's considered fast film and requires less light to expose it. Fast film is used for poor lighting conditions or for shooting fast motion, and in a perfect world, film wouldn't contain any grain, but the fact is, the faster the film, the more likely the developed image will show some visible grain. So choosing film is a matter of deciding how much grain you can live with and how long you can stand to have the shutter stay open, i.e. shutter speed. You might naturally want to use the least grainy film available, but the smaller the grain, the longer your shutter needs to stay open to expose the film. The longer your shutter stays open, the more likely you are to have a blurry image, which can be even more detrimental to your image quality than film grain. Just like camera controls, the industry uses standard film speeds, and they are 25, 50, 100, 200, 400, and 800. Going back to the analogy of the bucket of water, just like the bucket needs a certain amount of water to be filled, each film needs a certain amount of light for it to be exposed. With a film speed of 100, you would need twice as much light as film with a speed of 200, yet half as much as film with a speed of 50. Well, like shutter speed and f-stop, the VRay physical camera has a setting for film speed, and like a real-world camera, you'll get all the same qualities in the final image that you would get with a real-world image. The default film speed of 200 is the average film speed used in a real camera, and it's a decent choice for a typical daytime scene with partial to full sun. If you want to capture nighttime scenes or fast-moving objects without the excessive blurring, you should use faster films like 400 or 800. If you want to reduce grain in the image or accentuate the blurring effect of fast-moving objects, try a speed of 100 or less. Now, to bring all this together, we know that the shutter speed and f-stop settings control the amount of light that reaches the film, and you could use a wide range of combinations of these two controls. For instance, if we use a light meter in the real world and the meter tells us that a shutter speed of 1/125th of a second and an f-stop of 8 is the correct exposure, any of these combinations of shutter speed and f-stop would work, i.e. any of these combinations would allow in the same amount of light. Well, that does it for the three major areas that I wanted to cover here in Module 7. Now let's briefly review the most important points. The first feature covered, progressive path tracing, is really a nice feature for inexperienced users who just don't want to have to worry about a lot of settings to get right. But it's also good for experienced users. An experienced user that has a lot of time available for rendering might find it convenient to bypass a lot of the test renders and just put the rendering in motion and stop it when it's of sufficiently high quality. An experienced user who has a small amount of rendering time available might also find it convenient not to have to wait for an irradiance map to be calculated, as well as the entire image to be completed before having something that they can use. When this rendering method is used, the subdivision value needs to be set really high, and for a good quality noiseless image, it needs to be set so high that you have at least 1,000 sample rays for every rendered pixel. Also remember to disable anti-aliasing when using this option. With the VRay frame buffer, the track mouse while rendering option is great whenever you want to see multiple non-adjacent regions finish rendering first. And along the bottom of the VRay frame buffer are numerous icons that give you access to controls which you can use to make small adjustments in color levels, color curves, and exposure. You can actually change the image drastically, but I say small adjustments because you really shouldn't be making large adjustments here. If such large adjustments are needed, you should first attack the problem in other areas of VRay. Finally, the VRay physical camera is a fantastic feature like no other that allows you to produce a unique and realistic look to your renderings with all the great features found in a real-world camera. And this is a unique and advanced feature which only compounds the complexity of your lighting setup. But when you understand what all the major features do, you actually have a far greater amount of control over your rendered output, just like a photographer in the real world. Things like adding motion blur or depth of field can be handled automatically with a VRay physical camera, as well as numerous other qualities that weren't discussed here. So experimenting with some of these additional features might be worthwhile at some point in your work. And this concludes Module 7.